we've got a situation where we've got two functions, alpha and beta. This is the set A. This is the set B. And this is the set C. Alpha is a function from A to B. Beta is a function from B to C. It's helpful to make diagrams like this to visualize what's going on, even though you don't know what these sets are and you don't know what formulas there are for alpha and beta. There may be no simple formulas, in fact. We've got two things to do here, and initially, we're going to do a third thing later. First thing to do is that we want to prove if alpha and beta are 1-to-1, which you can abbreviate 1-1, then beta alpha is 1-to-1. Now, the first thing that's confusing about this is, what is beta alpha? Is it beta times alpha? Not in the usual sense of the word, it's not. I hope you realized that in doing the reading. In the usual sense of the word, beta alpha is not beta times alpha. Actually, in a new sense of the word, especially when we get into, well, even chapter 1 and 2, but especially chapter 5, we will actually think of this as a quote-unquote multiplication. But here it's not. Think of it as it's what's called function composition. Have you ever seen the circle notation before? Beta alpha could sometimes be written beta circle alpha. You ever seen that before? That circle is not a circle in the usual sense of the word. It's not a geometric object. It's a symbol that represents a binary operation like addition or subtraction or multiplication or division, taking two things and combining them to get a new thing. This is the function composition operator, you could call it. Function composition operator. Our textbook doesn't use that notation, but there are textbooks that do. It's just a way of saying I've got two things, in this case, two functions that I'm combining to get a new function. How is it defined? Beta alpha is where you apply alpha first, then beta. You work from right to left in this symbol. Beta alpha applied to some arbitrary element of capital A, call it little a, by definition is beta of alpha of A. It's like in calculus when you have a situation where you need to apply the chain rule to differentiate. Beta of alpha of A. That's what this function, that's its formula, you might say. Right there, assuming you have formulas for alpha and beta individually. Now, again, this is an abstract problem, so we don't have formulas. But we do have properties, and we want to verify those properties. We're trying to prove this function composition is 1-to-1. You can still do the proof in the same kind of way as last Friday's example, in the big picture at least. The details are different. Again, you don't have formulas like we did last Friday, but you do have assumptions. You always have to use your assumptions. So you could start by saying, suppose, say, A1 and A2 are elements of capital A, and I'll use parentheses for extra emphasis. Beta alpha of A1 equals beta alpha of A2. Beta alpha is one individual function that we're trying to show is 1-to-1. Again, it doesn't hurt. Maybe it's helpful to go ahead and write something like we must show. It's not necessary to write this, but if it's helpful to you, go ahead and do so. We must show A1 equals A2. That's what 1-to-1 means. If the outputs are equal, the inputs must be equal. For each output, there's a unique input. It's not the other way around, right? It's not for each input, there's a unique output. That's the definition of a function. It's easy to get that mixed up. Can we help? Is the vertical line test helpful here? No, correct? Because I don't have formulas for these functions, and they're not even necessarily ordinary functions like from calculus. These sets could be finite for all you know, and you could just be specifying how the elements get mapped. Maybe capital A only has two elements. Maybe A1 and A2 are it's only two elements, but we're going to show that they're equal actually. You've got to use what you are assuming. That's the way proofs go of mathematical facts. Okay, let's write a little extra here. Since beta alpha of A1 equals beta alpha of A2, how can I relate this to beta and alpha individually? I've got to use the formula for beta alpha. This means beta of alpha of A1 equals beta of alpha of A2, using the definition of function composition. Again, maybe a little bit of overkill, but it is important to at least write this somewhere. Should I use the fact that beta is 1-to-1 first, or the fact that alpha is 1-to-1 first? If we use the fact that alpha is 1-to-1, that assumption means, let me use different letters, that if alpha of x equals alpha of y, that implies x equals y. That's what the knowledge of alpha being 1-to-1 implies. We don't have a condition like that down here, because the beta is kind of interfering in a sense. The fact that beta is 1-to-1 means that beta of x equaling beta of y implies x equals y. We do have a condition like that. There's your x, there's your y. So you got to use the fact that beta is 1-to-1 first. The order does matter. Since beta is 1-to-1, we've got beta of something equals beta of something else. The something and the something else must be the same something. They must be the same thing. Alpha of A1 equals alpha of A2. Yeah, now we're almost home free. Since alpha is 1-to-1, A1 equals A2, and we're done. I could have also added some words in here. I could have said, since beta is 1-to-1, this implies alpha of A1 equals alpha of A2. Since alpha is a 1-to-1, this implies A1 equals A2. We are using the previous line. So yeah, it is a bit tricky. I'm glad you tried, but it is a bit tricky. You really do need the fact that beta is 1-to-1 first, because your implication has to be in the right form. We've got beta of something equals beta of something else, not alpha of something equals alpha of something else. Yes, you do have the alphas in there, and yes, there's an equality there, but the beta is kind of messing it up on the outside. Next, let's prove that if alpha and beta are onto, then the composition beta alpha is also onto. So we didn't do an example like this last Friday. So I was leaving it up to you to try to do some research if it wasn't clear how to do it. Let's think about both of these facts actually visually here to help us think this through. First, let's go back to the 1-to-1 case. We showed that if beta alpha of A1 equals beta alpha of A2, then ultimately A1 equals A2. Another way to think about that is that if A1 is not equal to A2, then ultimately these two things are not equal to. That's called the contrapositive of the original implication. We were trying to show that beta alpha of A1 equals beta alpha of A2 implies A1 equals A2. We did that. We did prove that implication, therefore we proved this fact here. But we can also try to prove it by the following implication. The contrapositive of this, switch these two things around and negate them. If A1 is not equal to A2, that implies beta alpha of A1 is not equal to beta alpha of A2. Visually, this can now be thought about in the following way. If I've got two distinct elements of capital A, A1 and A2, and they are different like I've drawn them, then when I apply alpha to them, the fact that alpha is 1-to-1 means I will get distinct outputs over here. Distinct inputs giving distinct outputs is another way to think about being 1-to-1. I purposely made them on the opposite side. Okay, it's not a big deal. This one's getting mapped down here, and this one's getting mapped down here. But the important thing is that these are different. That's the fact that alpha is 1-to-1. They are different, so when I apply beta to them, I get different elements as well. Maybe this one gets mapped over here, and this one gets mapped over here. So this is beta alpha, ultimately beta alpha of A1, and this is ultimately beta alpha of A2. Oh, excuse me. Switch it around, A2 and A1. With regard to being onto, I'm assuming each individual function is onto, show the composition is onto. What does onto mean? Give me any element of capital B. The fact that alpha is onto means there's some element of capital A that gets mapped to it. Give me an arbitrary element of capital C. The fact that beta is onto means there's some element that gets mapped to it. Those are two individual things that are true. How do I combine them to show the composition is onto? I have to start with an arbitrary element in capital C and show there's something in capital A that gets mapped to it. Well, it's just a two-step process. Use first the fact that beta is onto to say there's something here that gets mapped there. And then use the fact that alpha is onto this to say there's something here that gets mapped there. Not necessarily the same as that one. And ultimately, in the end, under beta alpha gets mapped over here. That's how you want to conceptualize it to help you. So let's go ahead and do that now in words. Let C be an arbitrary element of capital C. I'll go ahead and write we must show that there exists not an element of capital B, but an element of capital A such that beta alpha of A equals C. Here, initially, I'm not referring to the B at all. But when I do the process of using the fact that beta is onto, I'm going to need to refer to B. I'll go ahead and do that right away. Since beta is onto, what does that mean? It means there exists a little b in capital B such that beta of B equals C. What's my goal? My goal is to find an A. Well, this little b in capital B, that's like this point here. Now use the fact that alpha is onto, there's something in capital A that gets mapped to that. Since alpha is onto, there exists a little a in capital A such that alpha of A equals B. Are we done? Basically, but we really should write a little bit more. We're trying to show that equation is true. What's going to follow from these two equations? Therefore, beta alpha of A, by definition, is beta of alpha of A. Alpha of A is B, and beta of B is C. Done. Therefore, beta alpha is onto. I should have concluded the other proof by saying beta alpha was 1 to 1. Just go ahead and state your concluding fact. I think that's good style. Very abstract, but this is an important fact to know. These two facts, when you compose two functions, if both functions are 1 to 1, the composition is 1 to 1. If both functions are onto, the composition is onto. Therefore, if both functions are 1 to 1 and onto, the composition is also 1 to 1 and onto.